In this tutorial, we're going to answer a very interesting question from stoichiometry. Okay, so make sure you watch to the end. 2.83 grams of sample of amethyte iron were dissolved in a concentrated hydrochloric acid, and the solution was diluted to 250 cubic centimeter. 25 cubic centimeters of the solution was reduced with tin chloride, which is oxidized to that, to form a solution of iron 2 ions. This solution of iron 2 ions required that much of potassium dichromate solution for a complete oxidation back to iron 3 ions. So basically we have a few questions. The first one says, given the half cell reactions to be that, deduce the fully balanced redox equations for the reactions. The second part says reduction of iron 3 ions by tin. So these are the equations that we should deduce for the reduction as well as the oxidation of iron 2 ions. Then the last question requires us to calculate the percentage of iron 3 oxide in the ore. So before we get to do anything, we very much appreciate the given equation. So I'll start with the first one. Of course, the first question says, given the half cell reaction. So we've been given the half cell reactions. The first half cell reaction that we've been given is of tin, okay, plus 2 electrons gained, giving us tin 2 plus. Okay, so if you look at this equation, is it a reduction or an oxidation reaction? So look at the power. The initial power or charge of tin was 4 plus. So what do we have on the right hand side? So it's 2 plus. So that is reduction reaction. So now the first part of the question, we are taught to deduce the fully balanced redox reaction. To start with, the first part is the reduction of iron 3 ions. So want to write an equation showing the reduction of iron 3 ions. So what is iron 3? So if we say iron 3, we mean it should be iron with a charge of 3 plus. So this was reduced to what? This is reduced to, so we only have 2 ores of iron. So basically if it's being reduced, it's going to be reduced from iron 3 to iron 2. So we're going to have iron 2 with a charge of a 2 plus. Yeah. So we want to balance the charges that we have. So if you are moving from a charge of 3 plus to a 2 plus, so remember, reduction is indicated by the reduction in the oxidation or the charge of the elements or the ions. So what happened for this to occur? So we are saying it was a reduction reaction. So reduction also involves gain of what? It involves gain of electrons. So therefore the iron 3 had gained an electron for it to become iron 2. So we've come up with a half reaction showing the reduction. So now we need to give a fully balanced redox reaction showing what had reduced what. So we need to combine, because the question is saying the reduction of iron 3 ions by tin. So it's basically tin 2 which was what? Which was reducing. So basically if this is a reduction reaction and in the other part it is a reduction reaction, so what do we expect? We expect that according to the question it's tin 2 which was reducing what? The iron 3. So we are supposed to reverse that equation, the first half reaction. So if we reverse it, it's going to be, what are we going to have? We're going to have tin 2 plus, then giving us that. So in the actual sense, tin was actually being oxidized. So we're just supposed to reverse the given equation so that it matches up with what we've been given. Okay? So because the statement is very clear saying the reduction of iron 3 ions by tin 2 ions. So we've shown that. So now we also need to balance the number of electrons. So the number of electrons in the reduction reaction is a single electron. Then in this other reaction that has turned out to be oxidation, we have 2 electrons. So we have to multiply the first half reaction by a 2 and a 2. So we've now balanced the number of electrons, so that as we get to come up with a fully balanced equation, we can just add them. So for the left hand side, we're going to have tin 2 plus, which is in aqueous state, together with what? With iron 3 in aqueous state. We also have 2 electrons, which I'm not going to indicate. Then what else do we have? On the right hand side, we then have tin 4, of course in aqueous, plus that was also 2. So we have ion what? We have ion 2, which is also in aqueous. So now, notice that in my rating of my equations here, I have not shown the electrons. This is because if we write them on the left and the right hand side, they're just basically going to cancel out. So this is our first deduced equation showing the reduction of the ion 3 to ion 2 done by the tin 2, which is on the left hand side. So this is how you get to come up with a balanced redox reaction. So how do you get to answer the second part, which says we also need to give another balanced redox reaction, which is showing the oxidation of iron 2 by the dichromate part. So we've been given the half reaction of the dichromate already, which is that. Okay, so I can write it the way it is. So we've been given chromate there, dichromate. Okay, O7 2 minus. Then of course we know it is in aqueous state, plus 14 hydrogen ions, plus 6 electrons, giving us that, plus 7 water molecules. Of course that is in liquids. Okay, is in aqueous. So now we need to show the oxidation of iron 2 ions. So we now have iron 2 ions. So iron 2 ions. So we need it to be oxidized. So for it to be oxidized, it requires it to what? To lose electrons. So it's going to be oxidized to what? To iron 3. So now there was a loss of what? There should be a loss of an electron. So loss of an electron is shown on the right hand side of the chemical equation. So now we need to balance. We need to make sure that we have a balanced number of what? We have a balanced number of what? A balanced number of electrons in the two given half reaction, and the electrons should be on opposite sides. So if you check the first half reaction there, they are on the left hand side. Then in the second one, they are on the right hand side. So it doesn't mean that if the given one has them on the left, it doesn't mean that the second one should have them on the right. It's you being able to identify that. What are they saying? So like if you check the first one, what we had happened is we had to reverse it because basically it had involved the reduction of iron 3 ions. But in this case, it's going to be the way it is because we've been told that we are looking at the oxidation of the iron 2. So this is the way oxidation is coming. So now, if the first given half reaction, if the electrons were on the right hand side, we would have reversed it so that it matches up with the second one, so that they are on the opposite sides and we're able to cancel them out. So now in this case, what are we going to have? We need to balance the number of what? We need to balance the number of electrons. So in the first half reaction, we have 6 electrons. How many electrons do we have in the second one? So we just have a single electron. So we have to multiply by 6. So multiply by 6, multiply by 6, and by 6. So we now have a balanced number of what? We now have a balanced number of what? A number of electrons there. So now we would want to now combine the two half reactions. So if we get to combine, of course we do understand that the electrons are going to cancel out. So now on the left hand side, what is going to stand out is we're going to remain with a dichromate, of course in aqueous state, together with 14 hydrogen ions plus 6 iron 2 ions. So I've written it down due to lack of enough space. Then on the right hand side, we're going to remain with the chromate there in aqueous states plus 7 water molecules, of course in liquids, plus 6 iron 3 ions in aqueous state. So now this is the balanced redox reaction showing the oxidation of the iron 2 ions by the dichromate 6 ion. So we've now shown the balanced equations. Yeah. So we've had the first part of the question. So now let's get to answer the second part of the question, which is now saying calculate the percentage of iron 3 oxides in the ore. So we need to do that. How do you get the percentage? So we need to get the percentage of iron 3 oxide in the ore. So now, if we go back to the question is very clear. We've been taught 2.83 grams sample of amethyte ion So the amethyte ion is that. So we've been given its mass. So now we are dissolved in HCl and the solution was diluted to 250 cubic centimeters. So that is the first part of the question, which is giving us the actual mass of the iron ore. So now, from this other part of the question, it continues to say 25 cubic centimeters. So out of the 250 cubic centimeters of the diluted solution of the ore, we got 25 cubic centimeters. So it's like we just got a tenth of it. It's like out of 25 over 250 is 1 over 10. So we've just got 1/10 of it. And what did we do with this, with what we got? So now, this much was reduced. So now, this is taking us back to the F reactions that we had come up. And remember, what F reaction did we show? What F reaction did we show for the reduction of the iron 3 ions? What did we say? How did we write it? So we had shown it this way. So we had said it was actually that plus 10. So this was our first F reaction. So I'm not going to show the states. I'm just interested in the issue of balancing there. So we have 2 that. Okay. So this was the first reaction. This is what had happened to the 25 cubic centimeters that we had gotten. It had to be reduced with a tin 2 chloride, which I've shown there, to give us that. So this was the first F reaction that we had. So now from there, what else had happened? So this solution of iron 2 ions required stored. So we are told 25 cubic centimeters of a solution was reduced with 10. So we've seen how it is reduced to that. So now after that, they are saying this solution of the iron 2 ions. So now we had produced a solution of that iron 2 ions. So now it required what? It required 26.4 of the potassium dichromate, which is taking us to the other equation where we are saying where the iron 2 is reacting now. This other reaction so I write it. So we had 6 that. So this was the other F reaction which we had balanced. So this had given us that. So of course we had water. I'm not going to show it because I don't have enough space. So plus water at the end. Okay, I'll show it. Okay, 7 water molecules. So this is the second F reaction that we had balanced. So we're just trying to represent this reaction. Okay. So we need to calculate the percentage of the iron 3 oxide in the ore. So in the first part of the question, we've been given the mass of the ore itself. So now we need just to find the mass of the iron so that we get to do what? So we need to get the percentage of the pure ore from the total amethyte ore so that we get to see basically what we're going to have. So now we're going to move backwards. What are we taught? We've been told at the end of the question to say the iron 2 ions, which is this part, required what? It required 26.4, so I write that, 26.4 cubic centimeters of what? Of 0.02 more decimeter per decimeter cube. So this is the concentration. So we're going to move backwards. So looking at the question, we've been given what concentration and volume was required by the iron. So after determining, basically now, after we get to determine the number of moles of the dichromate that was required, we're going to use the mole ratios to determine the number of iron 2 ions that had reacted in this last part of the reaction. So now after determining how much had reacted in this reaction, we are now going to go back to the other equation. So now it's like now we have the number of moles that had reacted. So now if you look at these two, you're going to notice that basically what you have is what? They are in the ratio of 1 to 1. So the same number of moles that you're going to do reaction is going to be the same number of moles that were present at the start of the first reaction. So after that now, it is now going to be up to you to now determine the number of moles that were actually present in what? In the ore itself at the start. Okay. So let's get to do that now. We see what we're going to have. So erase there so that we get to have some space. So now let's get to determine the number of moles that went in dichromate. A decimeter cubed. So I'm sure we do understand that the number if you make the number of moles to be a subject, that is basically what you're going to have. So remember, we need to make sure that the units that we are using for concentration are matching up. What units are we going to work with there? So for the volume, we've been given cubic centimeters. For the concentration, we have decimeter cubed. So we need to make sure that we convert the cubic centimeters to decimeter cubed. And how do we get to do that? So we need to know that basically 1,000 cubic centimeters is equivalent to a decimeter cubed, or a liter. So we're going to have 26.4 divided by 1,000. So giving us the units to be in what? To be in decimeter cubed, which will now multiply with a 0.02. So we're going to divide both by cubic centimeters and multiply by a decimeter cubed, showing the conversions. Okay, so if we get to multiply that 0.02 by that, what basically are we going to have as our number of moles? So I'm getting 0.000528. So those are the number of moles that were present in the second reaction for the dichromate ions. So now, using the mole ratios, the dichromate ions are basically in the ratio of 6 to 1. So 6 to 1 to the ion 2. So now 0.000528 is what we have for the dichromate. How much can we have for the ion 2? So that would require us to multiply. So our x is going to be multiplied by 6. So I basically have 0.003168. So what do we have there? So what we've determined now are the number of moles of what? Are the number of moles for the ion 2 that had reacted in the second part of the reaction. So now that we've determined that, let's go back to the previous half reaction. So the previous half reaction is telling us to say what we had reacting was the ion 3 reacting with the ion 2, giving us what? Giving us the ion 2, which had gone to the fade of the second reaction. So this is what we're trying to say. The ion 2, which was reacting in the second reaction, is this much. So now, if we add that much coming from the first reaction, how much did we have of the ion 3? Because basically, this is what we started with. So since they're in the ratio of 2 to 2, so they're in the ratio of 1 to 1. So meaning that the number of moles that we've determined from the second reaction is basically the same number of moles that had started there from the 25 cubic centimeters of the solution that we had. So therefore, we are saying we add the same exact number of what? The same exact number of moles. So now, we need to understand something here. Where exactly is this coming from? Where was the ion 3 that was reacting in the first reaction? Where did it come from? So remember that at the start of the experiment, we just add ion 3 oxide there. Okay. So now ion 3 oxide is what we had. So this adds, first of all, adds to split for us to have the ion 3. So what had happened? So we had 2 of that. So that is the reaction that is showing how the ions had split. Okay. So we add that. Of course, we do understand that for the oxygen we add 2 minus of it. So now this is the reaction showing what had happened. So this is the source of the ion 3 that we had in the first reaction. So now, in what ratio are they to the ore itself, or the iron oxide? They are in the ratio of 1 to 2. So 1 to 2. So now, if for iron 3 we have 0.003168, how many moles are we going to have for the first one? So now notice this. So it's like the number of moles of the oxide is basically they gets to be doubled after the dissolution or after the ions split, they get to be doubled. So now, if we add that much of the number of moles, how many moles did we have for the oxide at the start of the experiment? So if you cross and multiply, we're going to have 2x, right? So we're going to have a 2x being equivalent to 0.003168. So now the actual number of moles that were present in the oxide in the 25 cubic centimeters will require you to divide by 2. So I'm getting 0.001584 what? Moles of what? The oxide, the iron 3 oxide that was present at the start of the experiment. Now, this is just 1/10 of what we have. It's just 1/10 of what we had. Okay? It's only a 1/10 of what we had. Why? Because we had only gotten 25 cubic centimeters of it. So now, if in 25 cubic centimeters that we had gotten to perform our reaction, if we add 0.001584 moles of the oxide, how many moles were basically present in the 250 cubic centimeters itself? So basically this is like in ratio of 1 to 10. So we are basically supposed to multiply by 10. If that is to become 250, it requires you to multiply. So even the other side, let's multiply by 10. Or you can cross and multiply, whichever works for you. So if you multiply by 10 there, basically the number of moles that we're going to have is 0.01584. So these are the number of moles that we had in the iron oxide. Okay. So now, how do you determine the mass? Because remember, at the start, in the question itself, we've been given what? We've been given the mass that was in here at the start of the experiment. They made the mass of the ametite, or the iron ore itself. So what do we get to do? Okay, so we have a number of moles. So now, what is the molar mass of the oxide? The iron 3 oxide. What is the molar mass of it? So of course, by the molar mass, it requires go to a periodic table, get the molar mass of each element there, then multiply by the subscript. So now the molar mass of the iron ore, after doing your calculations, is going to be 159.69 grams per mole. So now, that being our molar mass, we can determine the mass. So we understand that mass is given as a product of what? Mass and the molar mass. Sorry, the number of moles by the molar mass. So for the number of moles, we have 0.001584. Not really. So it's 0.01584. Then for the molar mass, we have 159.69. So doing your calculations, what basically are you going to have as your mass? So 159.69 multiplied by 0.01584. So after doing my calculations, the mass that I'm getting for the iron oxide is what? So I'm getting a 2.529 grams. So what is the mass I've gotten for the iron oxide? The iron oxide. So now, the ametite ion itself had 2.83 at the start. So that's what we had now. So now, for us to find the percentage, we have to divide and multiply by 100. So that much divided by 2.83 multiplied by 100. So I'm getting 89.28. Okay, so now if you look at the given information in the first part of the question, what was the highest number of the least number of significant figures? So we had 2.83, we had 250 cubic centimeters, we had 25.0. So the least is 250, which had 2. Okay, which tells us to say that our answer, even as 89%, is very much okay. So that is how we've answered our question. I hope you've enjoyed, and I hope you've understood how to go about this question. Thank you very much for watching.